Elon Musk will never step into the laboratory where Tesla Optimus is researched and developed without bringing along a new idea, a challenging question, or a decision that could completely change the project's direction. If it took humans millions of years to evolve the way they walk, then why can't Optimus do better in just a few months? That question is not merely a challenge, it is a command. This is how Elon leads, not by telling us what to do, but by making us see that it is something inevitable. After 4 years of working on the future's best homemaker, Tesla Optimus has already demonstrated just how immense its potential is for everyday human life. Stay with me in just 30 seconds. You will see footage Tesla never released publicly. Before we begin, please help us reach 15,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Optimus and the latest news. At the Tesla Lab, creativity is a dense atmosphere, permeating every hallway conversation and every round of testing on the freshly printed skeletal frames of Optimus's hands. Though these are not the final versions, they stand as proof of the constant evolution in perfecting what is considered one of Optimus's most critical components. With 24 degrees of freedom to achieve dexterity close to that of a human hand, they allow the execution of complex manipulations with an accuracy of up to 0.1 millimeters. We draw no strict lines between the software and hardware teams. A mechanical engineer can just as easily propose an improvement to a control algorithm, while an AI programmer might suggest changing the knee joint material to reduce friction by 15%. Elon Musk encourages this blend with a simple principle. Every technical limitation is an opportunity for creativity. By the end of 2024, a period of sweeping changes had begun. In just 4 months, Optimus went through 42 software upgrades and 6 hardware overhauls. Part of the reason came from what Elon calls the compressed evolution cycle. We don't wait until a system is fully perfected before testing it. Instead, we continuously feed in small improvements, allowing the robot to learn while operating. New 12-megapixel vision sensors, an image processor optimized to cut latency down to 8 milliseconds, multi-channel object recognition algorithms with 98% accuracy, all of these were integrated without disrupting the overall architecture. In January 2025, I witnessed one of the most spectacular changes, the hand-eye coordination system. Previously, Optimus could only determine the location of an object and move its hand toward it. Now, the robot can adjust its movement behavior based on direct feedback from its fingertips, just like how a human instinctively readjusts their grip when they feel an object starting to slip. This was not just a software update, we had to redesign the tactile sensing structure inside the fingertips, crafting it from synthetic materials with elasticity equivalent to 90% of human skin, and improve the micro-actuators to respond 35% faster, achieving a reaction time of under 10 milliseconds. The electronic skin, developed by researchers from the University of Cambridge and University College London, can be melted down and reshaped into complex forms. This technology senses and processes a wide range of physical inputs, enabling the robot to interact with the physical world in far more meaningful ways. Although the robot's skin is not as sensitive as human skin, it can detect signals from over 860,000 sensor channels embedded in the material, allowing it to recognize different types of touch and pressure, such as finger taps, hot or cold surfaces, damage from cuts or punctures, or multiple simultaneous contact points within a single material. Combined with the 22 degrees of freedom in hands that are the most advanced in the current robotics market, Optimus is already demonstrating an unlimited range of capabilities, with the ability to handle over 1,000 different tasks in real-world environments. In the laboratory, everything feels amplified. Here, Optimus is tested through standard exercises, sorting objects at a speed of 50 items per minute, assembling battery modules with 99.5% accuracy, walking on uneven surfaces with inclines of up to 30 degrees, and communicating through language and gestures with a fluency level reaching 95% of that of a human. Our workbenches are covered with high-speed cameras recording at 120 frames per second, force gauges with a sensitivity of 0.01 newtons, torque analyzers, and entire server arrays for simulations with a computing power of 10 teraflops. Software engineers often stand beside robot skeletons with their frames fully opened, simultaneously checking control circuits and modifying code in real time. There are no barriers between lines of code and mechanical components. But when Optimus steps into the real world, the story changes. In the factory, the robot must contend with continuous noise levels reaching 100 decibels, lighting conditions shifting from 100 to 1000 lux, and objects moving unpredictably at speeds of up to 2 meters per second. Humans may pass by, sometimes even interact unexpectedly. We realize that AI must not only be accurate but also humble, meaning it should be ready to yield, wait, or adjust its behavior to fit the social context, achieving a collision avoidance rate of 99.5%. In the lab, everything is controlled. Out there, the world is a chaotic system that Optimus must blend into. Elon often appears in both settings, sometimes stepping into the lab in the middle of a test, other times going straight to the production line to see Optimus working alongside humans. He has a habit of asking questions that seem impossible to answer on the spot. If Optimus can learn to assemble faster than an engineer after 1 week, why can't we teach it to do that in 1 day? That question forces us to rethink the entire AI training pipeline, from simulation to real-world data, from reinforcement learning to context-aware adjustments, reducing training time for certain tasks from 7 days to just 24 hours. I remember one February afternoon in 2025 when Elon Musk requested that we build a mock neighborhood inside the testing warehouse. Streetlights, signboards, small shops, even other robots pretending to be pedestrians. The reason was simple. If Optimus is only good in a factory, it will remain just a machine. If it can thrive on the streets, then it will truly be a part of humanity. That very evening, the mechanical team began assembling the modules, while the AI team installed traffic scenario processors and crowd behavior algorithms. Within just a week, Optimus was able to cross marked pedestrian lines, avoid bicycles traveling at 6 miles per hour, and recognize traffic light signals with 98% accuracy. Every time Elon spoke with us, I noticed one thing. He didn't care about comparing Optimus with competitors in the usual sense of winning or losing. He would only ask, "Is it good enough that your child would trust it?" That question changed the way we measured success, not by the number of tasks completed, but by the quality of the human experience when standing next to Optimus, with safe interaction rates reaching 99.9%. In March 2025, we conducted a special trial, having Optimus work alongside a team of technicians on the 4,680 battery production line. In the lab, operations are pre-programmed and tightly controlled. But in the factory, Optimus had to improvise when equipment malfunctioned, when colleagues gave hand signals instead of digital commands, when a pallet of batteries was placed slightly off its designated spot. The result was that the robot not only completed its tasks, but also suggested improvements to repositioning that optimized the workflow, something we had never expected to happen at this stage, boosting production line efficiency by 15% and reducing errors to below 1%. When Elon heard the report, he simply smiled. When it starts teaching humans, we're on the right track. That was when I realized his vision didn't stop at creating a capable robot. It was about creating a true collaborator, an entity that could observe, learn, adapt, and improve the systems around it, with the ability to handle over 100 different tasks. Workdays at the Tesla Optimus lab always begin with an open-ended question and end with a new prototype. Between those two moments lie hours of code revisions, 3D printing components, testing sensors, logging data, and heated debates. Creativity here doesn't come from having free time. It comes from constant pressure and an almost unshakable belief that everything can be done faster, better, with the goal of producing 5,000 Optimus units by the end of 2025. Looking back from early 2024 to early 2025, I can see clearly why Optimus keeps changing. It's not a reaction to errors or competition. It's the very nature of how Tesla operates. Try, fail, learn, and then improve. All of it happens at a pace that never allows you to stand still, with more than 50 hardware and software versions updated along the way. Elon never gives us time to be satisfied with the current build. Every time we reach a milestone, he asks, "Good, now what?" I leave the lab tonight as Optimus is being trained on dozens of new skills. They may sound small compared to walking the streets or assembling batteries, but to Elon, every action, no matter how minor, is an opportunity to optimize, to learn, and to make the robot more human-friendly, with a folding speed of 90 pieces of clothing per hour and 95% accuracy. And as the lab doors close behind me, I know that tomorrow will start with a new question, and Optimus will change again. Not because it isn't good enough, but because at Tesla, better is always mandatory. How does Tesla Optimus plan to move on any terrain? Let's start with the perception system, often referred to as the robot's eyes. Tesla has adopted a vision-only approach, eliminating the reliance on complex sensors like LiDAR or radar, similar to the full self-driving system used in Tesla's EV. Optimus is equipped with a high-resolution camera array, up to 12 cameras in Gen 3, that provides continuous image data streams at 4K resolution and 60 frames per second per camera. This effectively delivers nearly 1,000 frames per second in total, enabling the robot to process over 1 billion pixels every second. The onboard artificial neural networks, trained on an enormous dataset of up to 10 petabytes from indoor environments, enable the robot to analyze images in real time. Result: Optimus develops an occupancy grid, creating a digital 3D map with up to 99.9% accuracy. This map clearly distinguishes between free space and areas occupied by obstacles or nearby objects, such as humans. For example, in a small household with 3 to 5 people, including children and the elderly, the grid can scan and update the environment in just 50 milliseconds. This allows the robot to avoid collisions with a remarkable 99.9% success rate in simulation tests, drastically reducing the chance of impact-related falls for humans to just 0.1%. This quite evidently positions Tesla Optimus as the ultimate homemaker we've been envisioning. To enrich the occupancy grid, Tesla integrates visual markers, unique features tied to specific locations captured by the cameras, such as the edges of machinery or battery trays, found in a factory setting. These markers play a crucial role in determining and tracking the robot's position with sub-centimeter accuracy, even in low-light environments, thanks to an infrared camera. According to Elon Musk, the system has been upgraded to include over 1,000 markers per square meter, enabling Optimus Gen 3 to achieve twice the localization precision compared to Gen 2. However, vision is not enough. The robot must also maintain balance and move smoothly, especially considering that Optimus Gen 3 features around 40 motorized actuators, amounting to over 200 degrees of freedom when including secondary joints. This is where the simulation system comes into play. The Tesla team has integrated the robot's motion code with the autopilot simulator, a tool previously used to train self-driving cars across billions of virtual miles. Within this simulation, Optimus can test and optimize its walking style, select gait patterns, and adjust other parameters to safely navigate indoor environments. The simulation enables precise actuator activation with torque ranging from 10 to 100 Newton meters, ensuring that the robot maintains balance even on uneven terrain with up to a 20-degree incline. Test results show that Optimus achieves a 98% success rate in balance retention after 1 million simulated cycles, reducing energy consumption to just 2.3 kilowatt-hours for 10 hours of continuous operation. One of the greatest challenges is replicating the human ability to walk. For humans, walking is second nature, but for robots, it is a complex problem involving hundreds of variables: terrain, robot weight, payload, environment, and many others. Tesla began by developing a comprehensive digital model that includes kinematic properties, dynamics, and contact behavior. This model, combined with environmental conditions and the target destination, is fed into the planning system to generate a reference trajectory, a sequence of paths from origin to destination, extending up to 100 meters within a factory setting. The trajectory generation process consists of 3 main steps, making the system exceptionally efficient. First, the system plans a complete path from start to finish, represented by a curved white line in the demonstration video, with an average length of 50 meters and a planning time of just 100 milliseconds. Second, the path is divided into smaller segments, each approximately 5 to 10 meters in length for easier management. Third, the gait is finalized for each segment, including walking speed, up to 1.5 meters per second in Gen 3, as well as the type of footsteps and actuator intensity. The result is a comprehensive trajectory that combines the planned path with detailed footstep parameters, achieving a 45% energy savings compared to Gen 2, while maintaining balance even when carrying a 45-pound payload. In the demo video showcasing movement over uneven terrain, you can see the real-time center of mass tracking system, refining the trajectory to prevent falls, with an impressive 99.5% success rate. However, the real world is not an ideal simulation. It is dynamic and full of surprises. This is where motion control and state estimation systems become crucial. In an ideal world, the planned trajectory assumes a static environment, but in reality, conditions are highly variable. Humans move around, sometimes up to 50 people on a factory floor. Forklifts operate at speeds of 2 miles per hour, and subtle changes such as slippery floors due to grease may occur. These factors can destabilize the robot, leading to potential falls. What would you want Optimus to do for you if you could control it with your thoughts? Maybe it's cooking your famous recipe or reading to your grandkids. Share your ideas in the comments below and let's think about the future together. If you enjoyed this video, please give it a thumbs up and subscribe for more stories about the technologies shaping our world.